Yes. So yeah, thanks, Michal, for the nice introduction. Thanks, Michal, both, and Basha, to you for inviting me here and being here together with you for this lecture. I'm looking forward to spending these next 2 hours here with you. And so I picked a few topics which I think will be interesting, and some recent results and some introductions into the field of quantum simulation and quantum computing with fermions. So actually, let me start with this slide, this historic slide. Some of you might know this is the famous picture of Stern-Gerlach, where they basically were able to photograph for the first time the silver atoms in inhomogeneous magnetic field splitting. And actually, it's a nice side story. They were sending this postcard to Niels Bohr to congratulate him for the confirmation of orbital angular quantization. And we know, of course, today that that's not quite correct. Actually, what they discovered was the spin of the electron. I showed this slide just to show you, how far we've come. Today, we're in 2025. About 100 years later, and I think it's absolutely amazing about the possibilities, how we can manipulate spins, how we can manipulate particles at a level that was probably unforeseeable for the founders of quantum mechanics that we're celebrating this year with the 100th anniversary of birth of modern quantum mechanics. All right, with that said, let me actually jump in and say a little bit about what I would like to tell you today. I'd like to give you an introduction into the field of quantum simulation and quantum computing with atoms, ultracold atoms. Specifically, we're going to focus mostly on fermions in this lecture, but a lot of the techniques also generalize to bosons. And so I'll start telling you a little bit about our systems, how we prepare the states, how we detect the systems. Michal already mentioned we have this nice technique of quantum gas microscopy, which allows us really to take pictures of these many body systems in ways, I think, again, that were not foreseeable when I at least started entering into this field. I'll talk a little bit about applications in condensed matter physics on understanding strongly correlated electron systems. I think we're really at a very, very exciting time in quantum simulation of strongly correlated electron physics, and I'll try to give you some of the gist of what's going on there. And then I'll switch to, how we can use that to have digital gates with fermions and what the advantages could be to do that. And is a maybe last part after the break, or we'll see if we can get there even. I'd like to also show you how far we are with quantum simulations of polar molecules, fermionic polar molecules, and I'll give you at the end an outlook. All right, so let's get started and basically remind ourselves that today people in different communities are using these two approaches to study quantum many-body systems. On the one hand, we have analog quantum simulation, where we try to implement a Hamiltonian directly in our system, like say the atoms in the optical lattice, and we can look at the time evolution or ground state behavior of the system. And that's a very powerful approach because it makes very good use of the resources in your system. You can push the time evolution, you can cool to very low temperatures nowadays. And this seems like a very powerful approach, but of course it's non-universal. You can only study what we can actually build in the lab. And we try to refine that. But of course, we can only study that what we can do in the lab. Then there's, of course, the digital approach of quantum computing, where we try to have a universal operation by digitizing the Hamiltonian evolution, for example, into elementary gate operations. And amazingly, just a few elementary gate operations allow you basically to study any kind of universal Hamiltonian that you would like to study. That's, of course, great. But of course, we also know that if we really want to do this in an error-corrected way, for example, it's extremely resource hungry. So today, both approaches are studied, but there's been this myth around that analog simulation might not be robust. And there was this very nice paper I point you to from my colleague Ignacio Serracchi in Munich, together with Raul Trivedi, who actually showed there's a really big advantage of this quantum simulation approach because it's intrinsically very robust and stable. And one reason for that is that, even in the presence of errors, which can actually be extensive in our system, because we are for, physical applications actually measuring intensive quantities, we're not really sensitive to the full wave function of the system, which you have to get right for quantum computing. But here, actually, this measurement of intensive quantities like magnetization, for example, densities, or even like lower order correlation functions, That's actually very robust quantities. And even in the presence of extensive amount of errors, we can have something like a notion of quantum superiority, quantum advantage, and actually a very robust way to simulate these systems. Now, for me, my path into this world of quantum simulation started, as Michal was saying, with this phase transition from quantum, from a superfluid to a mod insulator, taking this weakly interacting Bose-Einstein condensate and making actually very strongly interacting gas of particles by putting these atoms into an optical lattice, making the kinetic energy of the particles very small, and thereby having them dominate the interactions between the particles. And that basically induced this phase transition to a mod insulator, and basically goes back to pioneering ideas of Ignacio and Peter, who kind of outlined this. So that's already quite a while back, and the field has moved quite a bit. And quantum simulation today, I think, really is a major research field across a wide variety of platforms. You can see people in ion traps, in Rydberg tweezers, superconducting devices, and of course, optical lattices. We're going to talk about mostly today, actually use this to do advanced kind of quantum simulations, studying very, very different topics. All right, so let's move to our system that we want to kind of investigate here in this lecture. And these are like atoms in lattices. And these optical lattices, you can see a nice picture from Ted Hensch's labs here in Munich, where he took 5 laser beams and basically interfered those 5 laser beams. This, of course, gives rise to an optical interference pattern. And this optical interference pattern, in the case of the 5 beams here, is this beautiful quasi-crystal. And you can already see the beauty of doing condensed matter physics in such a pristine environment of this optical lattice is great, because they're basically defect-free. And there's all the problems, a lot of the problems you have in real solids are often not present in our systems, and we can do many-body physics in a very clean environment. And then we can load either, fermions, bosons into these systems, or spin systems, study spin systems. And I've given you a few examples here. And typically we can also have the atoms not being pinned to lattice sites, but actually move around in these lattices. And I think the ability to study fermions is really unique to ultracold atoms. So you take a fermionic isotope, put it in these lattices, in trying to, for example, mimic the behavior of electrons in a real condensed matter system. And because most of our world is made out of electrons, there's, of course, an immediate advantage of doing this quantum simulation approach with fermions and not having to carry this overhead of mapping a fermionic problem onto a spin problem, which has extensive overhead and complicates your calculation. So here we can really do that directly. And the only other platform I know where you can actually do that are, for example, electrons in quantum dots, which are also used for simulation, quantum simulation of fermionic problems. All right, so just to give you a few scales, so you can realize through optical interference very, very different kinds of lattice structures. And for a long time, we thought, well, we have to interfere the beams under different angles to get to different lattice geometries. But nowadays, we are actually in the community, we found ways how to do that very efficiently in just a single experiment. So at a push of a button, we can really change lattice configurations, going from square lattice here to an hexagonal lattice, to a triangular lattice, a Kagome lattice, or a leap lattice that you can see here. And that's, of course, very nice, because we don't have to synthesize a material new to study, for example, new properties when we want to study a new crystal structure. And since we know that the crystal structure plays an essential role in the physics and also the dimensionality of the problem, we're really in a very good situation to have this, at a push of the button change between configurations. At the top, you see a few typical energy scales and length scales of these atoms in optical lattices. So you see the typical spacings. They are, of course, on the order of λ/2 when you interfere 2 laser beams. So typically in the micrometer range. Then there's the hopping scale, the tunneling motion between lattice sites. And then if you think of an individual lattice site being basically a harmonic oscillator, then you have trapping frequencies in the range of 10 kilohertz to a megahertz, and ground state extensions of 10 nanometer to about 100 nanometer in the system. And then we can put, of course, atoms or molecules into these lattices. And of course, the world would be pretty boring if they would be just non-interacting. So we really want to put interactions into the game. And by now, people are using very different kind of interactions. You can have collisional on-site interactions. You can have magnetic or electric dipole interactions. And we'll talk a little bit about the dipoles for the molecules in the end. You can also excite the atoms to very high-lying Rydberg states and then have extremely strong van der Waals Rydberg atoms interactions between them up to gigahertz energy scales. Or you can put them in cavities and basically have the light mediate all-to-all interactions between the atoms or molecules in the cavity. So this is typically what people do, and all of these things are explored. We're mostly going to focus on the collisional kind of on-site interactions that you can have in these systems. All right, so our goal is to study, the physics of materials, or for example, superconductors. So we really, in a prosaic way, we want to study the picture of electrons inside this material. We want to study, how we can take photos of the electrons moving inside a material. And that's, of course, a dream which probably, would be, I think, almost impossible to think about how to do that in a real material. But in our quantum simulators, we can do that. And here's a nice picture of this quantum gas microscopy approach, where you basically turn on laser light onto these atoms trapped in the lattice. You make the atoms fluoresce, or the molecules, and you detect the fluorescence of these atoms with a very good microscope objective. And this gives you capture the fluorescence, and then you can resolve each individual atom on different lattice sites. Each bright spot, each blue spot here that you can see here is an individual atom trapped on this lattice site. And you can see that we can detect these atoms with extremely good signal to noise ratio and have very good detection fidelities in the system. So we can do that in various ways. We can also change the geometry of our material, also the boundary conditions of our material. We can have, circular boundaries. We can have rectangular boundaries. We can terminate them with certain edge properties, which often determines whether the system can enter into a topological phase or not. We can also apply artificial magnetic fields. We can introduce frustration, dimensionality, and all of that is basically fully tunable at the push button, because we control the laser fields externally that create all these lattice potentials on top of the atoms, right? Okay, so one actually important detection technique for fermions is that you would really like to not only detect where the position of an individual atom is, but you really also want to detect whether it's a spin up or a spin down atom that is located on a certain lattice site. And in our case, let me give you one technique how we've been able to do that in the experiments that we're going to use. And that is the following technique. Imagine you have your 2D system here, where you have the physics going on that you want to study, a system of fermions, or spin ups and downs particles of atoms in our case, and you want to detect these now. So the way we do this is we take this physical system, and then only for detection, we actually apply a Stern-Gerlach separation. We split this single layer into a double layer, into one layer, into two layers. And we do this under the action of a magnetic gradient. And it comes back to this original Stern-Gerlach experiment. So it's the most controlled Stern-Gerlach experiment you can think of. And then what happens, like the spin up atoms move into the upper plane, the spin down atoms move into the lower plane, you separate them, then they're a little bit too close to each other, and you have to separate them over larger distances, which we do by a process called topological pumping. And then you've separated the spin ups from the spin downs over a larger distance. And then you can just focus your microscope objective onto either one of those layers. So either the upper layer, which contains the spin up atoms, or the lower layer, which contains the spin down atoms. You take a fluorescence image, as you see here, you reconstruct the occupations on the lattice, then you just put everything together, and then you actually got a snapshot, what we call a single snapshot of the atoms in your system. So you know where all the spin ups are, where the spin downs are, you know where sites have been doubly occupied, you know where holes are in the system. All of this becomes readily observable in the experiment. And these snapshots are basically then matrices that we can use then to give to theorists and, for example, calculate physical correlation functions in the system. So if you think about what we're actually doing in these systems, is like, think of the many-body wave function, the system being in a coherent superposition of different configurations. And whenever we take a photo, we actually collapse the wave function onto a single configuration in the system. Okay, so we don't know which one we're going to get in the photograph. This is random. And the only thing we can say how probable individual configurations are by, would be complex coefficients here, and the norm squared of that would give me the probability. But what I'm going to see in a single shot is a priori and not predetermined. And I just see one snapshot. And then I projected my wave function onto, for example, this state. And then I have to recreate psi, and I repeat. And then I measure again. And I recreate and measure again. Recreate psi, measure again. And you do this tens of thousands of times. And when you do this tens of thousands of times, what you end up with is probability distributions of configurations. So in the end, what the experiment tells us, how likely is it to get this configuration, the other configuration, and so forth. And that allows us, this probability distribution of configurations allows us then to calculate actually very interesting correlation functions. And I'll give you many examples of that during the course or during the lecture here in the following of the course. Now you might wonder, well, what about, these are complex numbers in principle here in front of the amplitudes of these configurations. So what about the phases? Where do they play a role? Well, a good question. They actually play a role in the, for example, currents that flow in the system. So the question is, can we measure these currents in the system, or can we measure operators where these phase factors actually matter? And one way to do that is the following trick. So imagine you have a physical system, which would be this square lattice that you can see here. And then just for detection, you can either observe the occupations of the sites in a spin and density resolved way. That's what I showed you before. But you can also project onto double wells just for detection. And now you can actually detect the orbital degrees of freedoms in these double wells. And we'll talk about what these are. And there actually these phase factors matter. So what kind of things can you measure here? You can think of this double well. Let's zoom in on a single double well. Okay, this single double well, it has a left side, has a right side, and you can think of it as just another incarnation of your two-level system. Just like having a spin up and a spin down would correspond to a left and right. And then, of course, means that the states in this double well of a single particle can be represented by basically a Bloch sphere describing the orbital degrees of freedom in the system. So the poles of the Bloch sphere would describe the occupation of the left and right sides. If you're here in the South Pole, everything on the right side. If you're on the everything in the North Pole, everything's on the left side. And if you're in the equatorial plane, you have a coherent superposition of being in the left and right well. And we know, of course, the equatorial angle determines the phase factor of this superposition. Now, what you can now do is, just as operations on the spin orbital Bloch sphere, you can carry out X rotations and Z rotations to change the states and measure the operator that you measure. And for example, just tunneling operations, they would just correspond to X rotations on this orbital Bloch sphere. And if you tilt your double well in a way where you introduce a detuning and energy offset between the two sides, this would actually correspond to a Z rotation in your system. And with this X and Z rotation, you can basically address any state on this orbital Bloch sphere, or taking it as a measurement device, you can measure any operator on this orbital Bloch sphere. We already talked about the operator that measures this Z-axis. That's just the Pauli's sigma Z operator that would be just corresponding to the density difference between left and right sides. And in the equatorial plane, the x-axis would correspond to the kinetic energy operator of your Hamiltonian of the particle in the double well. And the sigma Y operator would just correspond to the current operator of your particle on that double well. So that allows us to change the measurement basis and thereby measure currents, kinetic energies, and densities just as we wish. So let me give you a few examples how we do that. So how do we measure in the current operator? Because in the end, we always read out, when we do the fluorescence imaging, we always read out the density difference between right and left sides. But like if we interlace a time evolution of our system in between, we can actually see that if I'm projected into the double well and then just look at the non-interacting time evolution in the double well, this will actually give me the following operations. Yeah, just Rabi oscillations in my system here. At time t equals 0, I just recover the original density operator. density difference that I had. But if I weight, for example, a pi over 2 in my phase factor here in my tunneling operation, and basically what happens is that I see that this cosine term becomes 0 and the sine term becomes 1. And then actually what you see that the density difference you read out after waiting for a quarter oscillation period is just actually the current operator in the system. This is the current operator, and that's what you're measuring when you do this quarter oscillation around the x-axis in the system. The z-axis allows us also then to change around the zero-axis rotation by introducing a tilt here, and then you can measure just the density difference would give you the kinetic operator after doing this x operation first. Okay, and this is nice because it really allows us to measure current, for example, not only densities in the system, but it allows us to measure complex current patterns in the system. So for that, we actually imprinted onto the system artificially a current pattern where we have the phase differences of the wave function between different lattice sites given by these numbers that you can see here. So this denotes there's a pi phase difference here. And so this gives us a certain current pattern that we can now actually measure directly using this approach. And so this shows us here the measured experimental current pattern. This is what theory predicts, and we see that actually matches very, very nicely with the experiment. But we can also actually use it to do this in parallel. So we can change the measurement basis in parallel. So we can say we not only want to measure the densities, we want to now measure just the currents on all the bonds. And so then we would just do this X rotation that I talked to you about. We add a Z rotation, we can measure the kinetic energy. This works as global operations very nicely, and we can do this with rather high fidelity, these operations in the system. But we can also do this locally, and that's very powerful. We can also choose that locally, we only want to measure, for example, the current operator, and on the next double well, we actually want to measure the density operator. How do we do that? Well, we apply a local shift. For example, here, local Z operator with detuning, just a local tilt, which only acts on this one side here of the double well. It lifts this a little bit up in delta, but only on that specific side. So now what happens is that basically, if you look at the oscillations that would happen in this double well compared to this double well, if you introduce a pi phase shift through this detuning here, you can make the oscillations go in phase here and out of phase here by 180 degrees. And this is what you actually see here. By just doing this local operation, we can actually read out different operators with 180 degree phase difference in this case. You can use this actually also for advanced state preparation. So for example, if you shine this light shift onto this line of light and make the atoms here oscillate out of phase with this double well here, then you can generate after a suitable time evolution a pattern like this one where you have no atom 1 1 0 0 1 1 0 0 and so forth. And this is a kind of a snapshot of such a picture, and then averaged over many sites, over many realizations, you see we can really nicely create this. And by having more complex local patterns that you shine on the system, you can set up basically arbitrary complex density and current patterns initially, and that's very nice if you want to study, for example, non-equilibrium dynamics in the system and read out different operators. Just as a final thing, maybe before we switch gears, we can use this also now if we would have a system with flux. Imagine a large 2D lattice where we now apply an artificial magnetic field and we have flux now in the system. We can read out the currents of this large system really with single bond resolution. So here's actually 140 plaquettes in the system. So really large system that we measure in the lab, where we can on each individual bond read out the current operator and see, for example, when we apply this artificial magnetic field, we get something like these cyclotron orbits on these plaquettes where the currents, where the atoms now race around these plaquettes, if they're isolated plaquettes, and do these cyclotron orbits, and we can resolve them. So these are direct measurements. These arrows are direct measurements of this current pattern in the system. And I think you can already imagine this is, of course, fantastic if you want to study topological phases, you want to study edge states. We can do this now by looking at the current patterns with single site resolution. And of course, you can measure the statistics also of these current patterns. You can not only measure what the average current is, but you can really also measure current-current correlations. So how is the current on this bond correlated with the current on this bond, what is the statistics, what is the full counting distribution of this current operator. So we can not only measure the mean value, we can measure the standard deviation, the kurtosis, and all higher moments of the distribution by having access to these snapshots. All right, so let's move on. A few more things, but I'll skip this for now. Let's actually move on in really trying to do many-body physics with the systems of fermions and look at how we can apply this to interesting problems in correlated electron physics. Yeah? So the model of choice that we want to look at here is the so-called Fermi-Hubbard model. It's a very simple model describing the spin up and down fermions, the spin state indicated by this sigma here variable, the lattice site indicated by I. So the particles can tunnel through the lattice. So an atom with spin up can hop from this side to the next side with an amplitude t. And when spin up and down fermions come together on the same lattice site, they actually interact very strongly through this collisional on-site interaction. And they very nicely are described by this collisional on-site interaction. And through so-called Feshbach resonances, we can actually also tune this parameter u, so we can make this to be repulsive. So we can have the repulsive Hubbard model. We can tune it to attractive settings. So we have the attractive Hubbard model, or we can make a non-interacting model by just tuning this u to 0 using scattering resonances, so-called Feshbach resonances. Now at half filling, meaning that you have 50% spin up, 50% spin downs, filling up your lattice sites exactly. You can map this in the strongly interacting regime. You can map this Hubbard model onto a spin model, simply an antiferromagnetic Heisenberg model. So this more complicated Hubbard model can be described just as interacting spins, an antiferromagnetic spin model where the J is positive and basically given by super exchange interactions. So it's second order hopping that out of the Hubbard model generates this SI-SJ interaction between the spins on neighboring lattice sites. And the sign for fermions is actually antiferromagnetic. For bosons, it would be negative and ferromagnetic. So now the question that people we're really trying to understand better with these quantum simulators is, when you dope these systems, what is the interplay of these mobile dopants with this antiferromagnetic background? And this, you can see why this is important. You can see here in this phase diagram taken from a paper from Bernhard Keimer and Subir Sachdev on the cuprates. So the high TC compounds, the famous cuprates compounds, and you see they basically at zero doping all start out with such antiferromagnetic insulators, Heisenberg systems. And then once you dope these systems, then all these kind of interesting phases appear. There's the pseudogap, strange metal, potential superconducting phase here. And while we do understand more about the ground state nowadays from numerics, I think there's still many, many open questions connected to this that we would like to solve using the quantum simulation approach. So just broken down into a simple question, what you're trying to understand is, how do these mobile dopants in an antiferromagnetic background interact with that? So we'll see there's a competition between the two behaviors, and what kind of physics does this give rise to? So, okay, so let me show you how we do these experiments, or people in general in our field do these experiments. So we have the optical lattice. We can put fermions in there. We can shape the potentials by shining additional light fields onto them. And typically we do the following setup, where we have additional light potential on the atoms, which is shaped in this way. So everything is confined to a box that you can see here. Nice box, like nice homogeneous system. And then we like to introduce reservoirs here at the edges where the chemical potential is slightly lifted up, which would just correspond to a different light shift of our system. And then we have the central region, which is the region where we do the physics. And now by changing the light intensity, for example, we can change the depth of this physics region, this mu r, relative to the reservoir region. And this would be, in a real condensed matter setting, this would be something like applying a voltage to your material, which allows you to tune the chemical potential, and you tune in and out of different quantum phases of your system. And we can do the same thing here. So by just changing the light field intensity, we can change this mu r and tune out of different phases. And for example, for our fermions, if we tune into the right regime here, right chemical potential regime, we can realize strong interactions, strong repulsive interactions, this mod insulating region, which is characterized by a density of 1. So the density in the core of the system is pinned to 1. And here you can see again experimental measurements from that. The density is pinned to 1. And in the reservoir region where the density is lower, actually you see there it falls off. There we have a metallic region. And what's interesting that this interface between this mod insulator and this metallic region basically confined to single lattice site resolution. And we can really see this interface with single lattice site resolution. Now, this would be the average density, which is the outcome that you get by averaging over many of those snapshots. But you can also, since you have these snapshots, you can look at the variance. You can look at the particle number fluctuations on each lattice site. And this is, for example, the result of the variance, where you see that in this mod insulating regime, where you have 1 atom per site, you have a very low variance corresponding to an incompressible region of your system, and then connects to a metallic region on the outside. Okay, so we have established we have a mod insulator in the core. It has nice unit density. We know how to tune the chemical potential of our system, but do we really have an antiferromagnet? Well, for that, we can use the spin and charge resolve detection that I showed you before. Remember, by splitting these planes into 2 and then separating them and imaging the spin ups and downs separately. And if we do that, and calculate the spin-spin correlation function, we actually see that indeed we have very nice antiferromagnetic correlations basically extending over the entire system size. And we can now calculate the simple 2-point correlator as Z correlator, calculating, how is the spin on site I correlated with the spin on site J. And then, of course, we want to subtract, any average spin density that we might have. Now we can calculate this, and this is plotted here. This is these circles here. And then we can go to theorists like, for example, my colleague Lode Pollitt here in Munich, an expert on quantum Monte Carlo simulations, and they can calculate what the spin correlation curve should look like. And this is their theoretical prediction, the line, and you can see that matches actually perfectly with the experiment. And from this comparison to theory, we can actually determine what the temperature in our system is. So this gives us actually very good confidence about what we're preparing in the lab, and the agreement with QMC in the regime where we can do it also gives us confidence in the quantum simulation approach. But of course, we want to push this into regimes where basically this will fail, where basically we have no calculations anymore, and we really have to find out, we can discover something new. Now, one thing I was promising you was to have a better understanding of how holes interact, dopants, let's say we remove an electron out of the system, give rise to kind of new interesting physics. So let's just take the simplest case and look at a single removed electron, a single hole that is now in the system, moving in an antiferromagnetic background. And now what you see is if you have a hole here, what it can do, it can, of course, tunnel from this side to this side. That means the green spin moves in here. So you would have this configuration. Now it could tunnel one side more, so it moves over here. And then the red spin would have moved here. But you see already an interesting thing that the more this hole moves, the more it leaves behind actually a string of flipped spins, of ferromagnetically aligned spins. And remember, the spin model actually favored antiferromagnetic spin correlations. So these ferromagnetic correlations are very bad from a magnetic point of view of the Hamiltonian. They cost you a lot of energy. This means that this hole, from its kinetic energy point of view, it would like to delocalize, it would like to move throughout the system, but it's hindered in its motion throughout the system because of the magnetic correlations in the system, because if it would like to just continue moving, it would leave just an infinite amount of flipped spins behind. That would cost like an infinite amount of energy, so that can't happen. So this motion of the hole through the antiferromagnet, cannot happen indefinitely. And there's something like a confinement showing up. If you calculate the energy cost of this hole moving through this antiferromagnetic background, what you actually find in a very simple picture is that there's like a linearly increasing energy cost of the hole moving through the antiferromagnetic background. And this linear increasing energy cost. This should remind you of something in nuclear physics. This is basically what you also have in nuclear physics in quarks that give rise to confinement in mesons and baryons, right? in nuclear physics. So we also here then would expect new quasi-particles to emerge, new particles to emerge from this confining potential. And these new particles that emerge are indeed what we call magnetic polarons. So you can think of them as an original hole, a dopant, surrounded by a cloud of modified spins, of spin distortions in the system. And whenever this hole moves, it actually has to drag around with it this entire cloud of spin correlations to it. So that's basically our meson that is formed in this system. And here's actually a picture of such a polaron, this dopant surrounded by this modified spin correlation. So let me walk you through this graph because it's quite complicated. And it's actually a beautiful example of already a very highly non-trivial spin correlation function that we're measuring that you cannot measure in a real space, in a real condensed matter system. Why? Because what we're looking at here is a 3-point correlation function. So we're asking the following question: given that I find a dopant somewhere in the system, a hole, or in our case, this was a doubly occupied site, we call this a doublon. So given that I find a hole or doublon somewhere in the system, what are the spin correlations in the vicinity of this dopant? Okay, this is what this correlator expresses. So you find a hole at site R, and you then ask how are the spins correlated in their z direction at site R plus I and R plus J. And you see this is a 3-point correlator that you need to evaluate to get to this. But this is really the essence of what will show you the structure of the polaron. You need to measure this 3-point correlation function. Now there's a small c here. This means this is a connected correlation function. And so this actually tells you that what you're measuring is you're not interested what the background antiferromagnetic correlations were, and you're subtracting the background antiferromagnetic correlations in the system. So you really want to know what is the difference of having the impurity there, how are the spin correlations modified due to the presence of this dopant, and you're not interested in the background spin correlation. So that's where we like to use the connected correlators. We subtract out the antiferromagnetic spin correlations that are also there in the undoped system. We only want to remain with the ones that are there in the doped system. And then you get pictures like this. So we find a dopant here inside there, and then I can plot what the spin-spin correlations between the different sites are, and we encode this in these ellipses that you can see here, and the color code of the ellipses tells you how strong the spin correlation actually is. And you can see that you actually have a huge cloud surrounding this dopant where the spin correlations are modified. And this is exactly this distorted spin cloud that I was promising you that makes up the polaron in the system that we have in the system that is formed around such individual dopants. All right. We can compare to QMC. That's also good for the small systems and low correlations that QMC can calculate. But I think what's interesting is that we can now, since we have established the presence of polarons, we can actually look how their behavior is changed when we change the doping. Because we can not only change the lattice structure continuously, we can also change the doping continuously by just changing the chemical potential of our system. We can continuously change the doping in the system. And we can see how the behavior from very few individual dopants, where we expect the polaron, changes in a regime where we have very large degree of dopants. And so we basically can continuously check what happens when we go over from this small dopant regime, we have the polarons, and then we go to this large dopant regime, we go to this Fermi liquid regime. And we know from condensed matter measurements that here we are in the regime where we have kind of a strange metal where the charge carriers are actually the polarons in the system. And on the other hand, when we have very, very large dopings, we're back to a normal Fermi liquid in the system where the charge carriers would be the normal electrons in the system. And interestingly, see, we can really now have microscopic pictures where we resolve how this polaron breaks down as a function of doping. And we can pinpoint exactly this crossover regime of this polaronic strange metal phase to this more standard Fermi liquid electron phase in the system. All right, so actually, let me see if I want to go into this part here. Let me actually skip the pseudogap part. I think it's a bit too much. But let me just finish before we go into the break now and then take a few questions. let me say we're now, we're in a super exciting time on the field where now the lowest temperature measurements, which we've seen now from the Harvard group and Markus Kreiner's group, can really reach this 0.1 temperature regime in the temperature measured in units of the hopping. And this is very interesting because it allows us to access many phases that are poorly understood. For example, this pseudogap regime. At lower temperatures, we even expect like exotic ordering stripe phases to appear where, the dopants that you put into the system align along line patterns, form density waves in the system with interlaced antiferromagnetic domains. And I think we are now in a really unique position where we can combine this microscopic picture with this, fantastic phenomena and poorly understood phenomena in the condensed matter regime that people are putting together. And this really gives us for the first time the possibility to combine macroscopic measurements from the condensed matter world, like conductivity, compressibility, magnetization, together with these microscopic pictures of charge and density resolved pictures where we can resolve hidden order parameters, higher order correlation functions like this 3, 4, 5-point correlation functions that really give us completely new insight into the physics of these strongly correlated systems. Let me just actually, yeah, let me also skip that. Let me just mention that there's a lot of, just briefly, works from other people in the field. So there's like very exciting work. I don't know, Martin Zwirlein already gave a talk or will give a talk also in this series. He has beautiful results on the attractive Hubbard model, where he sees similar phenomena to what we've seen on the repulsive side. And there's really very nice work from Markus' group and Wasim Bakker's group in Harvard and Princeton from introducing frustration into the system and going from square lattices to triangular lattices and seeing how that actually changes the behavior in the system. And finally, also, I'd like to mention work in Zhanwei Pan's group in China, which is also, they're really scaling up these systems to enormous sizes where we can have millions of atoms now in 3D systems, also potentially getting very cold and trying to also extend these studies to 3 dimensions. All right, I think it's a good point maybe to take a break here. And
to do. So the question to Immanuel is, what is topological pumping?
Okay, so this is a process that was originally identified by Thouless, and basically is a very robust way how you can dynamically move charges or densities around in the system. For us, it basically means that we can time modulate our optical lattice potential in a simple way by adding another second lattice potential, such that you can separate the spins over very large distances. And while you do that, you always keep a gap in the system. So this process actually becomes extremely efficient. So the topological part really is a protection for the efficiency of the pumping. And you can actually show that this 1D plus time evolution, you can map actually onto the 2D system and think of it like a quantum Hall system. That's where topology comes in. So there was a kind of a mapping of this 1 plus 1D system to a 2D system by Thouless, who showed that this actually time modulation of your 1D potential can have some topological protection as long as you don't break this topological feature. Turns out that in practice for us, it's like super robust and super efficient. And that's very important because remember, for the detection, you want to separate the two planes and you want to really move all the atoms very efficiently when you separate them. You don't want to lose them on the way. And that's where this process actually enormously helps.
Okay, thanks. And there's actually one more question that came in the meantime. What are the limitations on the correlations that we are able to experimentally measure? I know that all two-side correlation functions can be found, which is enough to compute end-to-end quantum mutual information. So can the same be done with QMI involving more sides?
So in QMI, I don't know, but I can tell you what we can measure, and maybe then you can tell me what, later in the discussion session, what you have in mind. So what I showed you, we have to make a choice whether we want to make a density measurement or we want to make a current measurement. And if we want to make basically, but we can also mix those if we have local control in the system. But then once we made that choice and get these snapshots, you can, for example, in the density and spin and charge sector, that's how we call it. Remember, spin is like spin resolved, that tells you it's spin up or down. Density tells you the particle or not. And we just call this charge because in condensed matter systems, electrons carry charge, but just for analogy, just not to confuse you. So we can do any kind of spin charge correlator. So you can, like what I showed you, you ask, okay, given that I have a hole here, that's a density operator, how are the spins correlated around that hole? Okay, so that's a 3-point correlator, but we did that also for 5-point correlators, very higher order correlators. You can ask, for example, now, if you have 2 holes next to each other, how are the spins correlated around those 2 holes? So if you would have, let's say, Cooper pairs of those 2 holes, how would the spin environment around those pairs look like? That would be a 4-point correlator because you have a hole here, correlated with the spin surrounding that. So, and all these things become accessible. And I think what we're learning, and I think there's a huge potential for discovery also on the theory side here, but we're really learning that these higher order correlators are extremely important to understand these exotic phases of matter that people are finding, which, you know, they've had such a long time, such a problem understanding these phases, like this pseudogap phase that I showed you on the phase diagram, for example. And maybe that's now just a conjecture, maybe the problem was that people have just been looking with 2-point correlators and trying to understand the world of pseudogap phases through 2-point correlators, because first of all, that's the only thing that experiments could measure. And that's basically how people have been thinking. But maybe, you know, the reason why we didn't have a breakthrough there in understanding these systems is because there's more complex order, there are more complex correlation functions that characterize the order in the system. And this is where I think there's really a totally new window here of using this powerful tool.
So there is some hope for more than two-side correlation.
Absolutely. Oh, absolutely. We can basically, we've measured up to 5-6-point correlation functions in the system.
Great. That's amazing. Okay, you see, we have two more questions that are anonymous. Maybe people are simply a bit shy. So the first of the other 2 questions is, what exactly was the doping rate again, and how was it changed?
Okay, very good question. Let me go back in my slides. So the doping rate, we can very simply change by changing this chemical potential here. Okay, so remember, there's a reservoir here of atoms connected to the physical region in the center. And this chemical potential is like having the voltage on your material, and this voltage actually would control also the density in your physical material system of electrons that you dope into the system. And likewise in our system, by changing this chemical potential, we can have the density be unit density or tune away from this unit density by changing this chemical potential factor. And the way then in practice how we do it is just change the intensity of the laser light in the central region versus the laser light that hits this reservoir region.
Okay. And the last question, are the atoms stochastically loaded onto the 2-dimensional array of tweezers, or if the study involves any specific initial arrangement?
Very good. So there's a confusion here. So we'll come to the tweezer and lattices at the end, and also active sorting. Here's no active sorting. That's the magic. So the fact that you go to a phase where you have 1 atom per lattice site, it really happens through the many-body physics itself. We don't have to sort anything here. We start out with a metallic state, or when we do this mod transition for bosons, it would be a superfluid, which has order in the phase of the wave function, but complete disorder in particle space. So if we make photos, it looks completely disordered. It looks like nothing is ordered. But then when we go to this mod insulating phase, when we tune the chemical potential correctly and tune the interactions to repulsive interactions, we make this transition to this mod insulating phase. And there now every site is occupied by 1 atom. But we don't do anything by hand. It's really the many-body physics in the system that guarantees this. But I'll actually show you in the end an example of where we combine this, where we can actually also do this active sorting in the tweezers, but that would have different approaches. We can maybe then artificially assemble a mod insulator initially by sorting the atoms and then doing the many-body physics we want. But in this approach, this is really done by the system itself. That's a very good question, very important question. Yeah.
Yeah, can you imagine how many PhD students you would have to do that all by hand, one by one? Yeah, that's illegal.
That actually is pretty efficient. I'll show you in a movie
Ah,
in the end
great.
of the talk. All
Okay,
right.
so see, this question serves as a spoiler alert for the rest of the lecture.
Yeah.
Okay, so let's continue the lecture. Thanks.
Okay, so we have another half an hour, right? And then we have a final
Yeah,
discussion session
sure. I
sometime
think we
next.
should end by 4, including the
Yes.
other Q&A session at the very end. Yeah.
Sounds good. All right, so let me move forward again. And actually, so yes, and here we were. Let me go switch from analog to digital. And everything I've shown you so far falls into this realm of analog quantum simulation. But one could, of course, ask, can we also do something digital and have more power there, thereby in studying different phenomena than the condensed matter physics phenomena? And this is especially important, for example, if you think about doing chemistry or molecular calculations on a quantum computer. Wouldn't it be advantageous to actually do that with the fermions itself? Because typically the problems you try to calculate, the quantum chemistry problems, are fermionic problems in nature. And it turns out that's actually true, and there have been quite a couple of people working on this version of fermionic quantum computation. And the basic idea, the advantage is, of course, that if you use fermions right away, you have the correct exchange statistics built into the system automatically, and that greatly reduces the overhead of your computation. And one can, of course, now ask, how good can we implement this basically in our systems? And there was this very nice proposal, for example, from also one of my co-workers, Philipp Preis, here at MPQ here in Munich in Garching, where he basically showed that you just need very few local operations. Many of those are introduced already to you. You have these super lattices that I talked about, where you have these double wells. You can do these tunneling operations. You have the tilts in the system. So all of these are kind of single qubit operations in the orbital degree of freedom. Remember, this double well can be considered as like a spin system, but in the orbital degrees of freedom. So combining all these single qubit orbital degree of freedom operations that I showed you before, together with gates, with interacting gates, I'll talk about those in a second, you could basically build such a fermionic quantum computer. And the question, of course, is, how good can we actually be in these systems with these fermions in the optical lattice? Now, in terms of gates, what options do we have? What kind of fundamental 2-qubit gates can we have? So there's the gate that most of you might be familiar already with, what we call a swap gate. This basically, if you start out with a spin up and down fermion in the well here, it swaps over into up-down fermion on the right-hand side. And the way this works through the Fermi-Hubbard Hamiltonian is that basically you have a second-order hopping process where the blue spin hops onto the neighboring sites. But remember, there it has to pay an energy U, because there was this repulsive energy when they sit on the same site. So it can't stay there. So either it hops back, so it comes to the original configuration, or the red spin now actually hops to the opposite side, and this realizes this swap operation. So this is a second order process. And you see you have to hop once, hop twice, and there's an intermediate energy scale, which is this intermediate state of double occupancy, and you can immediately calculate the amplitude for such a process in second order perturbation theory. That's just t squared over u, where t is the hopping matrix element and u is the interaction energy. And now there's another interacting gate you can build, which is what we call a pair tunneling gate, which basically starts out with a doublon on each side already. This, remember, this carries energy U in the system. And now if a single particle tunnels away, that would also not conserve energy. So it can't do that alone. So the second atom has to actually follow in pursuit. So these pairs are like repulsively bound and tunnel coherently as a pair from one side to the next. That's the other gate we can have. We call this a coherent pair tunneling gate. And if you have either of those swap or pair tunneling gates, then you can realize all these operations and have all the ingredients for this kind of fermionic version of your quantum computer. So let's see how good this actually works, how good our 2-qubit basically operations are. And the first thing we can do is just to look at the quality of our swap oscillation. So we make a single double well. We place spin up-down fermions in there, and we know from the Fermi-Hubbard Hamiltonian, just from the collisional interactions, this should swap back and forth, up, down, up, down, up, down, up, down, up, down. We just monitor this, and we see actually really we have extremely long-lived exchange oscillations with very, very low damping rates. And if we calculate something like a fidelity of this process, of this continuous evolution, it's not yet a gate, it's just a continuous time evolution, this turns out to be like really, really high in the 99.95% fidelity range. So that's already very, very encouraging. And what we're kind of blown away also, you know, when you use this swap operations, the coherence times of the entangled states that you generate at half the evolution time are actually extremely long. So this is what we call a square root swap gate, where you know, in a swap gate, you swap from up, down to down, up. But if you would stop in the middle, you would create an entangled state, a superposition of up, down, and down, up, a Bell state. And you can now ask, how long lived is this Bell state? Well, we can do that. We can check the lifetime of this Bell state by basically doing so-called singlet triplet oscillations. If you apply a magnetic gradient field across the double well, you can convert the singlets into triplets during this time evolution, and you can read that out very efficiently. And we see there's basically no damping on this. So over time scales of a second. Yeah, actually, we measured this now more quantitatively, and the lifetime of this entangled state was measured to be more than 13 seconds. And if you contrast that with the number of exchange oscillations we have, this gives us a nice ratio of coherent gate operation to lifetime of the entangled states, easily in the 10 to a few 10,000s of operations that we can have in the system. Here's just shown this gate operation, this double well. Now just the dynamics in the double well resolved more in time. So we just let the atoms do this swap operation in a time evolution. We can see how we swap from up down to down up and back to up down. And if we stop in the middle, we kind of generate this superposition state of up down and down up, the entangled state in the square root swap operation. And now if you want to compare this to gate fidelities that one has in the system, then you really have to do this in a pulsed operation mode. So a gate is not a continuous time evolution. You really have to do this in a pulsed operation where you apply these square root swap gates, and then you apply multiples of these square root of swap gate operations, and then you can estimate what the fidelity of your 2-qubit gate operation is. And we do this averaged over 66 qubit pairs, so quite a large system of qubit pairs in the system, all read out together. And we can then see from this decay of the contrast and the fidelity over applying these square root swap gates multiple times that we actually turn out to have extremely competitive fidelities in the range of 99.8% collisional fidelities. Now, I just want to put that in contrast to the ones that people have seen in Rydberg gates, for example, in the Lukin group, for example, 99.55%, Kaufman group on strontium atoms in 99%. So these collisional quantum gates actually turn out to be extremely good. And together with a single qubit operation, I think we have a really good basis for realizing these also digital quantum computers in the system. Just to put this all on a graph here, so I think we've seen the coherent oscillations. They give us super high fidelities, but they're really not quite as fair to compare to in terms of gate operations. If we really run this in kind of gate operation mode, then we place ourselves basically here with somewhere between 99.7 and 99.8 2-qubit gate fidelities. And I think, you know, this was just our initial shot. So I think there's a lot of room also for improvement here. Physically, we could easily go, physical limitations of this 2-qubit gate should be really an order of magnitude higher even than what we've realized in this first run for the experiment. Okay, so this is nice because it really, I think, opens the path in the future for realizing such fermionic quantum computers, a completely new computational paradigm, which is, of course, especially well suited for dealing with any fermionic problems in material science or quantum chemistry. All right, as a final thing, maybe I just want to touch briefly about a completely different topic on quantum simulations with polar fermionic molecules, and just show you what people have been doing there. So this is actually a very long-standing effort in the community, and actually people in Poland, and Michal also has played a very important role in understanding these systems, these complex molecules. And compared to atoms, you know, they're just already so much more complex that one might get scared as an atomic physicist. They have these vibrations, rotations, all kind of phenomena that come into play in addition. But if we take, let's say, polar molecules made out of two different atoms, they can have also an electric dipole moment. And this electric dipole moment is, of course, very nice because it gives you an electric dipole-dipole interaction, which then scales like d squared over 1 over r cubed, and should give you a really interesting physics in the many-body level when you have access to this longer ranged interactions in the system. However, there has been a big problem in the field that basically when these molecules collide, they tended to get lost. And this is what people call the mystery of sticky collisions, that what one assumes what happens is these molecules collide, they form complex tetramers, and these tetramers just have so much phase space that they basically get lost and never come back and dissociate into our two polar molecules. And so for a long time, the field has been stuck and really not moving forward in being able to cool these molecules to high phase space density, simply because of the fact of these sticky collisions and these losses. And I think still it's not so clear what's going on, but we found a way around that. First of all, let me remind you how we can actually make this harness this dipole moment, this electric dipole moments of the molecule. So in the lab frame, typically when we apply no electric field, there's no dipole moment, only in the molecular frame. But if we apply an electric field, we can mix different rotational levels and align the molecule with the electric field, and then the dipole moment becomes visible of this molecule. So just applying an electric field gives rise to this dipole moment that you can now see. But you not only can do this with static fields, you can also do that with microwave fields. For example, if you apply a rotating microwave field, you can actually set this dipole moment into rotation. For example, with a circular polarized field, it would just give you rise to the circular oscillating dipole moment in the molecule. And again, depending on the strength of the electric field of your microwave, you can induce an effective dipole moment that then can give rise to attractive, effective interactions between the molecules. Now, how can that be used to remedy this problem of collisional losses, of molecular losses? Well, let's think of the blue-detuned rotating microwave field. So here are the rotational states of the molecule, the ground state, and the first excited rotational state. And let's imagine we apply a blue-detuned circular polarized microwave field to the system. So then if we think of the two molecular potential curves that we can have in the system, this would be two molecules in the J equals 0 rotational state. This would be one molecule in J equal 1 colliding with a molecule in J equals 0. And we see because of the dipole-dipole interaction, we can have these attractive and repulsive branches in the system. And typically that would give rise to kind of strong losses in the system. But if we go to a dressed state picture now, where we mix these states of J equals 0 and J equals 1 and shift this potential curve up, and because of the blue detuning, this delta is positive, we shift this up, we can create a crossing here. And because of the interactions in the system, we can turn this into an avoided crossing because of the finite Rabi frequency we're applying to the system. And this avoided crossing now creates a potential molecular curve, which basically does not allow molecules that come close to each other to penetrate into this lossy region where all the bad things happen. So at short distance, all the bad things happen, the tetramers form, the molecules get lost. But if we could rather have them still collide, but keep them at larger distances, we could avoid these losses. And this is what this microwave shielding allows you to do. It creates a potential energy curve over which the atoms now are hindered to go to close distances. And this works actually very efficient, but you also should think of this now, this creates like a huge shielding core around 50 nanometer size, which is like much larger than the typical distances atoms approach each other. So atoms typically have this core around 5 nanometers. Now this avoided crossing is created at intermolecular distances of 50 nanometers. So it's really a huge kind of fat kind of core that is in the system. And you can think of such gases more like helium, where you also have such large core potentials in the system. Now, you can ask, how well does that work? Well, it turns out that worked spectacularly successful for the field. So when we applied this shielding and in the system, we could immediately reduce the inelastic bad collisions between molecules, suppress them by a large amount, but still have very strong elastic collisions in the system. And this allowed us basically to apply standard evaporation techniques to cool the quantum gas, the molecular quantum gas, in our case, the fermionic molecular quantum gas of sodium-potassium atoms, down to quantum degeneracy. Now the lowest that we reach is about 0.25 T/TF in the system that we can cool these gases to. And just to show you that it's not, a lucky shot, immediately this technique was picked up by other groups, and Sebastian Will's group in Columbia, you might have heard about this very nice result, was then the first to do this bosonic molecules and immediately realize basically a BC of molecules in sodium cesium atoms. So this is really a fantastic technique, a universal technique that allows us to cool these molecules now to quantum degeneracy. Now, the rotating microwave field actually also gives us a lot of possibilities in changing the molecular potential curve. So here I have plotted the molecular potential as these molecules approach each other through different orientations. They can collide with each other. And now by basically tuning the ellipticity of the microwave field, going from a circular polarized microwave field to an elliptically polarized microwave field, we can really tune these molecular collision curves, these molecular potential curves, to a very high degree. And we can actually tune, for example, the depth of this molecular potential curve and thereby introduce bound states into this molecular potential. In these bound states that are now introduced into this colliding molecular potential curves, then can give rise again to scattering resonances. And these are so-called field-linked resonances. And they've been predicted first by John Bohn in the field, and we've been able to detect these field-linked resonances with these ultracold polar molecules directly in our system by just changing, these ellipticities of the microwave field. And in contrast, maybe to some of you who know Feshbach resonances, which basically you have to be lucky to get in atoms, this is a universal technique, I think, that should apply to any polar molecule that you can have in the system. Now, why is this interesting? I think we're now, in a very interesting regime where we now have these fermionic molecules that we can bring to low temperatures. We can induce kind of p-wave dipolar interactions between them. And maybe we can hope to get dipolar p-wave superfluids. And if we could do that in 2 dimensions, we'd have topological p-wave superfluids that we can realize in the systems. So far, we're not at that point because temperatures are a little bit too high. But if we believe our theory collaborators, that should happen at around 0.2 T/TF. And that's not too far away from where we are in the experiments, in current experiments. All right. So let me just then close off and show you a few things where I think, the field is heading next. So I showed you in my talk a lot of ways how to do quantum simulations in the analog way, focusing today on fermions and optical lattices, but you see this all across with ion traps, superconducting qubits, everybody doing that. And of course, you have the other digital mode. And I think maybe for now, the best way to push forward to using this for fundamental science and new physics is to harness both modes. So basically maybe use digital mode for preparation and readout, and then analog mode, for example, if you want to study the time evolution in the system, which can be much more efficient than trotterizing a time evolution using a digital approach. So I think really combining these 2 techniques now in a hybrid operation of analog and digital seems to me one of the most exciting things to do right now to push forward in realizing new things and understanding quantum phases of matter in new ways. And I think one particularly interesting direction that comes to the question that was asked is combining the optical lattices with tweezers. So you might have heard about the tweezer arrays, where you trap individual atoms in focused tweezer beams, and then you can move these tweezers around. That works very nicely, very powerful, but the distances between the tweezers is typically much larger than the spacing of atoms in an optical lattice. And that means there's typically no tunneling motion of the atoms in the tweezers. So they are far apart. You can use Rydberg interactions to have them interact, but they can't really move around. And we really want the atoms also to move around to study this interesting, for example, Hubbard physics that we have in the system. So can we think of combining these 2 worlds with each other? And there, one of the pioneers was Adam Kaufman in Boulder, was the first ones to show this. And this is very nice. And let me show you our Munich results in this direction. But let me first show you a picture that you can really scale this to gigantic sizes also now. So this is a picture of optical lattice with strontium atoms with over 25,000 lattice sites and over 10,000 atoms in this lattice. So each individual blue point is like a single atom in this lattice. And this just shows you that, combining both worlds really, I think, is also a very powerful way in going forward in scaling neutral atom quantum computing, quantum simulation technology to much larger system sizes than what I've shown you. And I think this is going to be a big push in the next years to come. But we can also combine that and really, the world of tweezers and lattices and really move around, as was suggested by one of you in the questions, we can move around atoms in the optical lattice through tweezers. So we can pick up an atom and move it into a specific position here on the lattice and keep it stored there over time. And that actually has allowed us to have a continuous operation of an atom array by basically detecting whenever we lose an atom here on the side of the storage zone, we can just pick up a new atom from a loading zone and bring it into the side of the storage zone to fill the defect. So let me show you actually a very nice animation showing that. So what you're going to see here in this movie is on the left-hand side, we see the stochastic loading of the atoms into the tweezer. On the right-hand side is the array in the storage zone. And whenever an atom gets lost in the organized storage zone here, sometimes you see an atom going black. We just pick a new one up from the stochastically loaded tweezer zone and bring it into the zone here to fill up that defect and make that register work again. And that's, of course, I think a crucial kind of technology component, both for long-term continuous operation for doing quantum computing with neutral atoms, but also simulations and also metrology. If you think of having such arrays continuously there, building clocks with very, very long interrogation times or continuous operation times without dead times in the system, I think all this is now conceivable. And lattices combined with tweezers, I think, offer a unique possibility of doing that with huge scales of system sizes. And if you ask how large can this system be, this is over 1,000 atoms in the storage register here. And it's actually only size of this register is only determined by the loss rate and how many particles, what the loading rate is. So if we, these were first experiments where we weren't even so great in loading the atoms in a high loading rate into the system. But if we improve on the loading rate and reduce the loss rate to state-of-the-art numbers, which we think can readily be achieved, you can really think about arrays of tens of thousands of atoms being continuously operated in these systems. All right, so that wraps up my lecture, but let me just give credit to the fantastic team of people here in Munich who've been doing the work with me. On the one hand, we have really, on the Fermi-Hubbard model, fantastic theory collaborators, Antoine Georges, Alex Witek from Dresden, Antoine from Paris, Annabelle and Fabian here in Munich, Eugene Demmler in Zurich, St. Lode also here in Munich, working on the simulation theory using different numerical approaches that we can benchmark against the quantum simulators we have in the lab. And that's been a very, very fruitful collaboration. Here's our lithium team, the Fermion team, which produced most of the results I showed you. The senior PhD students now, C and Johannes and Petar. The team is now led by Titus. And Timon has moved on to Strathclyde, and Thomas was a long-term postdoc with us, very successful, and actually moved on to a permanent position in Paris now. And the initial orbital degrees of freedom rotations, this was done on the cesium experiment together with Monika Eidelsburger. And there, basically, the main player was Alex Imperto, who did most of the experiments on the cesium machine. Just briefly, the molecule machine, the final results I showed, this is the team of Xinyu, and the main persons there who did the experiments was Xinyang Chen, and now the senior PhD students are Sebastian and Shrestha, who have taken over. All right, with that, thanks a lot for having me with you. I leave you with this nice picture of Munich. And it indeed is a sunny day today, so it's indeed not a fake picture. We're a nice sunny day today. I hope you too have a nice sunny day. Thanks a lot for your attention.
Well, oh, wow. Thanks for this incredible lecture. Thank you very much. We are still waiting for the questions. We encourage everyone to input their questions in the Q&A section. But in the meantime, we actually have Three questions from our co-chairs. So let me ask you them in the meantime. First one, can we already say that these simulations have reached quantum advantage, meaning that the results from state-of-the-art experiments can no longer be modeled theoretically?
Yes. So, okay, I never push in this direction because this is a touchy subject, because provable quantum advantage, I think with these systems, we can never say, because tomorrow somebody genius could come around and have a fantastic numerical methods, but we're definitely challenging the most advanced numerical methods today. I mean, for the fermion simulations in the ground state, QMC is nice for 2D systems, but doesn't like so much doping. So once you get to too large dopings and too low temperatures around point T, 0.2, T over hopping, QMC starts to fail, basically. At least the versions, the unbiased versions we know of. Then there's the other version we used, is called METS, minimal entangled typical thermal state method, that Alex was using. This is also a very nice method, but it's more confined to stripe-like geometries. So it can't handle so well 2D, full 2D geometries. So I think the nice thing is now, of course, we can use these systems to test all these numerical methods against each other and try to learn together and push forward. And I think that's maybe a more fruitful way of thinking of this, at least how I think of this, as trying to claim raise the flag of quantum advantage. And yeah.
So more of a synergy of theory and experiment than a race.
Yes, I think that's, there will always be one ahead. We're challenging each other, and that's good.
Okay, actually, the second question from Michał really ties in great into what you said, and it has to do with dimensionality. So,
Yes.
are there any plans in your group or in other groups that you know of to implement such systems in 3 dimensions, in such sizes? Yeah.
Yeah. So we actually started out in 3 dimensions. All our first experiments were in 3D. So making 3D systems is not really the problem. The problem is more if you want to use this detection techniques of quantum gas microscopy. When you want to image with wavelength resolution, your depth of focus is also only wavelength resolution. Okay, so that means a 3D system, we would have to use tomographic techniques where we cut out a slice, we image that slice, then we, image another, cut out another slice, image another slice, similar to what you do in MRI, for example, imaging, to reconstruct 3-dimensional systems. So answer realization is not so hard. Detection is the hard part, which is why we mostly focus on 1 and 2D for now.
Okay. Okay. Okay, actually, we have 2 questions from the audience, so let's maybe tackle these first. Can you elaborate on the combined use of a tweezer array and an optical lattice? Is it primarily to introduce mobility to atoms trapped in tweezers?
I would put it the other way around. The tweezer can actually speed up the cycle time of our experiments tremendously, because we don't have to wait and cool the systems until they, organize into these mod phases. But we might be able to assemble them by hand and do that actually very, very fast. So it could be more that, we can assemble systems in a lattice, also with very interesting initial state configurations that would not occur naturally. Since we choose where we want to put each atom, you can just tell me whatever configuration you want. Let's say you want a defect line of atoms, or you want a domain wall or something, or 2 domain walls. We can just assemble that, and then we can look at the time evolution, for example, how that system behave. So I see more the power in this direction. And so the mobility would be one aspect, but more like using the tweezers to enhance, build interesting Hubbard systems.
And like you've mentioned during the lecture, to fix some defects. That's the one
Exactly.
part
You
I like
fix
a
by
lot.
hand, you fix a defect. Yeah.
Yeah, that's
Reduce
really
entropy. So basically, a cooling way of actively, assembling low temperature systems.
yeah. Okay. The other question is, how close is the Fermi-Hubbard model to simulating real high TC superconductors like cuprates? Which steps are expected in the direction towards more real quantum simulations in this regard?
Yeah, very interesting, and I think it's very close now. So, okay, now a real cuprate is a much more complex beast than, of course, what we have in the lab. Okay, so let's be clear. What we simulate is the Hubbard model, the single band Hubbard model for now, single band Hubbard model on different lattice geometries that you can have. But people believe that the essence of high TC superconductors is captured by basically, for example, square lattices with next neighbor hopping, to what people call T prime hopping. Okay, so if you have T and T prime hoppings, people believe that that's the essential ingredients for superconductivity. And I think we're very close to to achieving that. And even if you don't have that, but I would not focus too. I mean, superconductivity is one interesting aspect, but I would put it in a much more bigger framework. These quantum phases of these electrons. There are many competing and interesting quantum phases. Superconductivity is one which is interesting for technical reasons, of course, but I think in terms of its nature is very well understood. But of course, we want to understand what do we have to tune microscopically to get there. And this T prime coupling, I think people understand, is very important, the diagonal hoppings. And I think people are thinking very carefully how to do that in the experiments and how to also implement that. So I won't take too long. I think in a year or so, we'll also see that.
Wow, what an estimation. Okay, great. One more question, maybe more connected to the other of our co-chairs of this series, is what do you think about condensation in solid-state systems? Do you maybe see some opportunities there that are maybe harder to achieve in the atomic systems, or some other ways that you are especially looking forward to?
You mean, for example, in exciton polariton systems or
Yeah, or photon, or
states?
yeah, these kind of systems, yeah.
This is super exciting. I think their strength is more in, for example, open systems, open quantum systems dynamics. What I don't see so well in those systems, but maybe one has to think more about it, and I just didn't think careful enough about it, how to realize these strongly correlated phases that we have here. So mostly what you have in those systems are wave functions, BC, mean field states. There's some gain, some loss. So you can send up basically wave equations with gain and loss for those. But this leakage of light out of those systems, or the finite lifetime, is of course very detrimental to realizing these highly correlated and highly entangled phases of matter, because they are destroyed by any information leaking out of the system. But I think one maybe just needs to think more, and I'm not an expert on that field, but I think it's super interesting direction also to think about that.
Also quite synergistic. Probably things can really easily be translated from one to the other, but also, it's just another opportunity.
Yep.
Okay, we have another question from the audience. Could I ask if the lattice parameter is in nanometer level, not micrometer level? Is that still meaningful to combine it with optical tweezer?
Okay, so let's think first of the scales. So if I take the shortest space optical lattice I can do is by taking two counter-propagating laser fields, which give me a spacing of the standing wave, the maxima in the standing wave, by λ/2, right? So we can calculate that straightforwardly. So that would put us, typically we use 1064 nanometer laser beams. That would put us in a spacing from lattice side to lattice side of 500 nanometers. So that's very typical. That's what people like to use. People also use green lasers and make optical lattices. Then you are basically 500, half of that, then you are 250 nanometers. So that's typically the scale we have. Now with tweezers, we can't bring them so close to each other, because with tweezers, basically then we have interference between the tweezers that occurs. And it's actually that will spoil the quality of the potential between the tweezers. And so that's one problem. And so really controlling the potential, when you bring them very close, you make them tunnel very nicely. This has turned out to be extremely hard. So people have tried this. Wasim Bakr has tried this. Selim Yochem has been doing beautiful work in Heidelberg, bringing also Cindy Regal in Boulder, bringing tweezers close to each other and then having particles tunnel between them. Very hard to control the quality of the potential. And the lattices, somehow the beauty of the lattices is that they have all this built in. Okay, the interference pattern is perfect, and it doesn't need fine tuning. It just is great by itself.
Okay, and I think with this beautiful summary, since there are no more questions, let's conclude today's webinar. Let's all thank Immanuel once again for his magnificent lecture today.